All right, this is the back of the review sheet. Also another time-consuming video. Skip ahead, skip forward, whichever you need to see. I actually think I'm going to start with the math part at the bottom. I think you need more help with that, and then I'll come back to drawing all of this because that's going to take quite a bit of time. So we're going to start with number 32. It's a little backwards, but I think more people will need help with that than the other. So a compound has an empirical formula of CH3 and a molecular mass of 60 grams, and it wants to know what is the molecular formula. So we have to first find the mass of the empirical formula. So I have one carbon with a mass of 12.011. And then I have 3 hydrogens, each with a mass of 1.008. So they have a mass contribution of 0.0324. And I'm going to add that together to get my mass of my empirical formula. So it's 15.035 grams. So I have to take this molecular mass and divide it by that. So 60 divided by 15.035 is 3.999, so we're going to call that 4. Then this is going to be my multiplier. So I'm going to take CH3 and I'm going to multiply it by 4. So my molecular formula is going to be C4, H, 3 times 4 is 12. That is going to be my molecular formula for that problem. Number 33 says calculate the percent composition of each part. And if you remember, percent composition, part divided by the whole is what our objective is in getting to this. So for aluminum, there are 2, and I'm going to round for this just to make it go a little bit faster. So aluminum is 26.982. We're going to call that 27. So 2 times 27 is going to be a mass contribution of 54 grams. And then oxygen, I have 3 of those. I'm going to round that to 16. So that's a mass contribution of 48. So when I add those 2 together, my total mass is 102 grams of this whole molecule. So I want to know part divided by whole times 100. So 54 divided by 102 times 100 is going to give me 52.94%, and then 48 divided by 102 times 100 is 47.06, and the 2 should add up to be 100. So then the final math problem is if a compound contains 5.92% hydrogen, and we're going to take this and we are going to convert it into the number of moles for each of these things, for hydrogen and oxygen. So hydrogen is 5.927 divided by, I'm getting the molar mass from the periodic table, 1.008. So 5.927 divided by 1.008 is 5.88, and that's going to be moles. And then for oxygen, I have 94.07% or grams divided by 15.999. And that gives me 5.88 again. This is going to be a nice one. All right, so looking at this, my mole ratio is the same. If I divide each of them by themselves, I have a 1-to-1 ratio of hydrogen to oxygen. So my bracelet is bothering me. So my molar, or my empirical formula is simply HO. So we need to know that was my empirical formula, and then it wants me to find out what my molecular formula is. So I've got to take and find the mass of HO. So hydrogen 1.008, oxygen 0.999. So the mass is 17.007. And then I'm going to just divide 34.01, so this is my molecular mass, divided by my empirical mass, divided by empirical, and that's going to give me my multiplier, which is 2. And so I take this 2 and I multiply it times this. So 2 times HO is going to give me H2O2. And this is my molecular formula. All right. So you can stop there if you want to, or you can stay tuned for all this fancy drawing we're fixing to do. All right, so lots of repetition, lots of checking yourself, lots of vocabulary in this part. So each time we're going to start by listing the element with its valence electrons, and I'm going to shorten this, and so because I have, let me change this format, 1 times 4 equals 4, I have 2 oxygens times 6 equals 12. So when I add those together, I have 16 valence electrons. Okay, I have to draw this in order to know the shape and to be able to tell a lot of other things. So this one we have done enough. You should have just kind of memorized that it is, sorry I drew those too close together, that it is linear. And this is what the structure would look like. And so because it is linear in nature, we automatically know that the molecule is going to be nonpolar. And then we're going to use this electronegativity chart a lot. I'm not going to keep showing it, but you have this handy to be able to do this. So oxygen is oxygen is 3.5. and carbon is 2.5. I'm going to go ahead and write these like this because it's going to help us when we start looking at, oh, it's linear, we didn't really need to do that, sorry. So 3.5 minus 2.5 is an electronegativity difference of 0.1. So the bonds are polar, but the molecule was not. This top bond is a sigma bond. The second bond is a pi bond. So here I have 2 sigmas, and I have 1, 2 pi's. This shape is linear, and the bond angle would be 180 degrees. So we're just going to go down this one side, then we'll go back up the other side. So same format. Phosphorus has, oh my goodness, I'm drawing a blank, 5 valence electrons. And because there are 5 chlorines, I have to multiply 5 times 35. And I have 175 valence electrons from chlorine. So when I add those together, my total valence electrons is 180. So 180 valence electrons. Phosphorus is one of my exceptions, and so it's going to make phosphorus 1, 2, 3, 4, 5 with all of my lovely chlorines, each having an addition, or each having 7. That cannot be right. Is it really right? I did it times 5. I knew that wasn't right. That didn't seem right. Sorry about this right here, guys. 7 times 5 is 35. I made a huge mistake. 7 times 5 is 35. This number here should be 35. I don't know why I multiplied it again. So 35 plus 5 gives me 40 valence electrons. That is much more reasonable. 40 valence electrons. Okay, so looking at this crazy configuration, because my bond angles are not all equal, well, sorry about that. Okay, so this one, the shape, because all of the satellite atoms are elements, are the same. They all cancel out, so the molecule would be nonpolar. And then we're going to look at our electronegativity chart to see if the bonds are. So chlorine is 3.0, and phosphorus is 2.1, so they have an electronegativity difference of 0.9, so the bonds are polar, but the molecule is not. Every single one of these are single bonds, so there are 5 sigma bonds and 0 pi bonds, and this is trigonal or triangular by pyramidal. The angles are both 120 or 90. Okay. Carbon tetrachloride has 4 valence electrons from carbon, and chlorine, there are 4 atoms times 7 valence electrons each, for a total of 28. So add those together and you have 32 valence electrons. Because all 4 of these satellite because of all 4 of these atoms being chlorine around the outside, this is going to, they're going to all cancel each other out. And so all of these are going, the molecule itself is going to be nonpolar. Everything cancels. And then, because if you were to look at your electronegativity differences, chlorine is 3.0 and carbon is 2.5. There's a difference of 0.5. So in all of these, everything's pulling away towards chlorine, and there's no winner, no net direction, so the bonds are nonpolar. So this one happens to be nonpolar and nonpolar. Again, these are all individual single bonds, so I have 4 sigma, no pi. This shape is tetrahedral, with the bond angles all being 109.5 degrees. Okay, beryllium is one of those exceptions. So when we're drawing this, you got to kind of keep that in mind. So Be has 2 valence electrons, and there are 2 hydrogens, each with 1, so that's another 2. So I'm only going to have 4 valence electrons total. And I'm going to have Be with an H going each direction. And this is going to be a nice linear shape. So if we look at beryllium, 1.5 is beryllium, and hydrogen is 2.1. So 2.1 minus 1.5 is an electronegativity difference of 0.6. So everything is pulling out towards the hydrogens, but I don't have a winner in this situation. And so I have polar bonds with a non-polar molecule. I have 2 single bonds, so that's 2 sigma, no double or triple bonds, so no pi bonds. This shape is linear with a 180-degree bond angle. Okay. Boron is another one of my exceptions. Phosphorus was an exception. It had 10. It was okay with 10 valence electrons. So boron has 3 and will be satisfied with only having 6. And iodine, if I have 3 of those, each with 7 valence electrons, that's a total of 21. I have 24 valence electrons. And if we draw this, remember this is one of my exceptions. It's one of those that make the nice triangular planar shape. And each of these iodines has 7 valence electrons. They only have the one that is being shared. All right. So then if we look at the electronegativity difference between the bonds, iodine has a 2.5 electronegativity, and boron has a 2.0 electronegativity, so their difference is 0.5. So the bond's going to be polar, but if we were to draw, iodine is our winner. And because each of these angles because everything on the satellite is all the same, nobody's winning in the electron tug of war, so the molecule is non-polar. So polar bonds, non-polar molecule. I have 3 single bonds, so I have 3 sigma. There are no double or triple bonds, no pi bonds. This shape is triangular, planar, and the angle is 120 degrees. Okay, sulfur is another one of mine that will have an exception. So sulfur has 6 valence electrons, but it's okay having 10 or 12. Fluorine, there are 6 fluorines, each with 7 valence electrons. So that's 42 total from fluorine for a total of 48 valence electrons. So sulfur and each one of these are going to share with a fluorine. So since all of these satellite atoms are the same, there is going to be, it's going to be considered balanced, so the molecule itself is nonpolar. And then if we look at sulfur and fluorine's electronegativity differences, fluorine is 4, sulfur is 2.5, so 1.5 is the difference. So the bonds are definitely polar. All single bonds, so I have 6 sigma, no double or triple bonds, so 0 pi bonds. This is one of those fun, unique shapes. It's an octahedral. And the bond angles are 90 degrees. All right, so this is one of those fun polyatomic ions. We've got to make sure we remember that extra electron right there that it gained when it bonded with an ion. So nitrogen has 5 valence electrons. There are 3 oxygens, each with 6, so that's a total of 18. Plus I have just that extra electron that I gained. So I have a total of 24 valence electrons. So this is where you got to be really careful when you're drawing, and you make sure that you get them all. So nitrogen could double bond with any of the oxygens. I'm just going to choose this oxygen. So 2, 4, 6, 8. That oxygen has 8. And then the 2 extra electrons that nitrogen normally has as lone pairs on top is going to bond with these other oxygens here, or not bond, but it's just going to transfer to those other oxygens. So, you know, normally there's these 2 electrons up here on nitrogen. One of them came down here, the other one came over here. It's sharing, or sorry, one of them came to this one. This guy got his extra electron because this is a polyatomic ion, and so it's got a negative charge. So this overall molecule, because this is a triangular planar, and I've got oxygen all the way around, the molecule itself is going to be nonpolar. And then if we look at the nitrogen and oxygen differences, nitrogen is 3.5, oxygen is 3.0, so a difference of 0.5. So the individual bonds that you see there are going to be polar, so polar bonds, nonpolar molecule. And then here I've got 1, 2, 3 sigmas, and I only have the 1 double bond, so I'm going to have 1 pi bond. All right. The very last one, if we look at it, drawing out and figuring out all of our electrons, we have 2 carbons, each with 4, so that's 8 valence electrons. Bromine, there are 4 bromines, each with 7, so that's 28 electrons. So I got a total of 36 electrons. I'm going to just check my math because I'm super tired. I want to make sure I didn't mess that up. Yep, I'm good. So 36 valence electrons. So carbon is going to have a double bond in here. And then from there, you're going to end up with each carbon having a bromine attached to it. And then we got to put all our extra electrons around bromines. It's a lot of electrons. This is not a shape that we know, so we're not going to fill in the shape here. But if we look at it, everything pulling away around from the outside edges and things like that, the molecule itself is a balanced symmetrical molecule, so it's nonpolar. And then if we look at the electronegativity difference between bromine, which is 2.8, and carbon, 2.5, that's only a difference of 0.3, so the bonds are also nonpolar. And if we look, this one's going to be a little tricky. So I've got 1, 2, 3, 4 single bonds, and then this first one right here is also going to be a sigma, so there's going to be 5 sigma. And this second bond that's within these double bonds, that's going to be our 1 pi bond. And we're not going to worry about those either. Final question. Do any of the molecules above have more than one resonance structure? If so, why? Resonance structure means there's more than one way I can draw it. Your polyatomic ions are your key for that. So NO3 minus has it because you can draw it several ways. It can be drawn more than one way. Okay, so that is why. So I'm going to just sketch it here. It's not going to be drawn correctly, but I just want you to visually see. I didn't put any of my electrons there or anything, but I could have also made this oxygen be my double bond, or I could have made this bottom one, right? Any of those would have been considered correct. And, you know, I didn't put all these extra electrons. Oops, I even forgot that oxygen. I just wanted you to know and realize that resonance means there's more than one way to draw it. All right, good luck.